Quantum field theory predicts the behavior of a single electron to 12 decimal places. Match the measurement to the prediction, and you'd know the width of the United States down to a human hair. Nothing else in science comes close, and the mathematicians keep telling the physicists it shouldn't work. Tonight we walk into the strangest secret in modern physics, a theory that predicts the weight of empty space wrong by a factor of 10 followed by 120 zeros, a calculation its own inventor called hocus-pocus, and $1 million problem sitting inside the equations of every particle accelerator on Earth. If this fascinates you, subscribe. The panic isn't that quantum field theory is wrong. The panic is nobody knows why it's right. Let's begin. Pick up your phone and look at the screen. The glow reaching your eyes is electrons in the display dropping into lower energy states, emitting photons, which strike the cone cells in your retina. Every step of that process is described by one theory: quantum electrodynamics, a branch of quantum field theory. Here is what that theory can do. Take the electron's magnetic strength, a tiny property that determines how the particle behaves in a magnetic field. Physicists have calculated this number using quantum field theory. They've also measured it in the lab. The two numbers agree to 12 decimal places. Imagine you stretched a measuring tape from New York to Los Angeles. That's about 2,400 miles. 12 decimal places of precision on that distance would mean being accurate to the width of a single human hair, somewhere in the middle of Kansas. Nothing else in science comes close to this. Not chemistry, not biology, not general relativity. So you'd think quantum field theory must be built on the cleanest, most rigorously proven foundation in human knowledge. A theory this accurate must be solid all the way down. It isn't. Here's the strange part. In the year 2000, the Clay Mathematics Institute listed 7 problems they considered the most important unsolved challenges in mathematics. Prize money of $1 million for each. One of those 7 problems asks whether quantum field theory, in a specific form called Yang-Mills theory, even makes mathematical sense. As of today, nobody has claimed that prize. The question is still open. Stop and feel the weight of that. The theory we use to design particle accelerators, to predict the behavior of matter at its smallest scales, to build the transistors inside every computer. Mathematicians are still asking whether that theory is even logically consistent. One of the people who invented modern quantum electrodynamics was a physicist named Richard Feynman. Brilliant, playful, impatient with nonsense. Near the end of his life, Feynman said something extraordinary about the technique he'd helped invent. He called it, in his own words, a dippy process. He said the mathematics required was hocus-pocus. He said it should have been illegal. And yet it works. That's the paradox. Every morning in physics departments around the world, professors stand in front of students and teach quantum field theory. They write equations on boards. They guide students through calculations. Most of them never mention that the moves they're making are, strictly speaking, not on solid mathematical ground. They don't hide it. They just don't dwell on it, because dwelling on it would slow down the work, and the work keeps producing correct answers. There's a quiet agreement among physicists. The theory works. Don't poke it too hard. Get the predictions out, compare them to experiments, publish the paper. If something breaks, deal with it then. But over the past few years, the cracks have been getting harder to ignore. New measurements, old problems that refuse to die. Calculations that should give simple answers but give infinity instead. Mathematicians writing papers with titles like "How Hag-Tied is Quantum Field Theory Really?" and the uncomfortable truth is starting to surface in private conversations at conferences, we built the most accurate theory in the history of science, and we still don't know why it works. To understand how we got here, we have to start with a very strange idea. The idea that changed everything about what we mean by the word matter. For most of human history, we thought the world was made of stuff, little things, atoms bouncing around in empty space, clumping together into bigger things, molecules, rocks, planets, people. If you could shrink down small enough, you'd see tiny solid objects zipping around like marbles in a jar. That's the picture most people still carry in their heads. Quantum field theory quietly demolished that picture about 90 years ago. Here's the replacement. Imagine the entire universe is filled completely and continuously with invisible substances, not air, not ether, fields. And the word field here has a specific meaning. A field is something that has a value at every single point in space. A temperature map of your city is a field. Every location has a temperature. The wind across a meadow is a field. Every point has a direction and a speed. Now imagine fields that fill the entire cosmos, one for electrons, another for photons, the particles of light, another for quarks, another for the Higgs, more than a dozen of them overlapping, occupying the same space at the same time everywhere. Here's the radical part. What you call an electron is not a little ball travelling through space. An electron is a ripple in the electron field, a small localized disturbance in that invisible cosmic substance, moving from place to place the way a ripple moves across the surface of a pond. Light is the same. A photon is a ripple in the electromagnetic field. When you turn on a lamp, you aren't shooting tiny bullets out of the bulb. You're creating disturbances in a field that was already there, already filling your room, already present in the emptiest vacuum between galaxies. Think about what this means for your own body. You're not, strictly speaking, made of particles. You're made of excitations in fields. The matter in your hand is a specific pattern of vibrations in the quark fields and the electron field. The pattern holds together because these fields are coupled. They can exchange energy through other fields, like the photon field and the gluon field. Your body is, in a very literal sense, music. A standing wave in the fabric of reality, playing itself for about 80 years. This idea didn't come from philosophers, it came from physicists trying to solve a brutal technical problem. In the 1920s, the new quantum mechanics worked beautifully for slow particles, but it fell apart at high speeds. Einstein's relativity demanded that particles could be created and destroyed. Energy could turn into mass. A theory of fixed particles couldn't handle that. So physicists switched the starting point. Don't start with particles, start with fields. Particles come out as a consequence. And once you make that switch, something strange happens. The field doesn't just hold particles, the field has its own behaviour, its own energy, its own restlessness, even when no particles are present. Which means empty space is not empty, not even close. If the universe is a stage filled with invisible, overlapping, vibrating fields, then the curtain is never really down. Even the darkest corner of the cosmos with no stars, no atoms, no radiation, is still a place where every field in the standard model is present, still humming, still ready. Which brings us to a thought experiment that first revealed how full the empty really is. Picture a perfect cube about the size of a shoebox. Walls made of the strongest material physics can imagine. Walls that let nothing in and nothing out. No light, no heat, no atoms, no radiation. We place this box in the deepest void between galaxies, millions of light years from the nearest star. We wait. Inside that box, what's left? Classical physics gives a clean answer. Nothing. The box is empty. Its energy is zero. There's nothing to measure, nothing to feel, nothing to detect. Quantum field theory gives a very different answer. The box is teeming. Here's why. Remember, every field in the universe, the electron field, the photon field, all the others, is present everywhere. That includes inside our box. You can't build a wall that keeps fields out because fields aren't like air. They're not something that flows in through the gaps. They're part of the geometry of reality itself. Wherever there is space, there are fields. Now we add the quantum part. In quantum physics, nothing can sit perfectly still. There's a rule called the uncertainty principle, and one of its consequences is that any system with the lowest possible energy state never actually reaches zero. A vibrating string, a swinging pendulum, a trapped atom. Push them down to their lowest state and they still shiver. It's built into the fabric of how quantum things behave. Fields obey that same rule. The photon field inside our sealed box can't sit perfectly still either. It jitters. Not because something is shaking it, because stillness at the quantum level is forbidden. So inside the empty box, the photon field is trembling in place. The electron field is trembling in place. Every field in the standard model is trembling in place. All at once, all overlapping. The box is not empty. It's a symphony of silent fluctuations. And here's where it starts to get uncomfortable. These fluctuations carry energy. Every jittering field contributes a small amount. When you add up all the contributions from all the fields, at all the possible wavelengths, well, we'll get to what happens when you add them up. Let's just say the number is large. Troublingly large. For now, focus on the picture. The emptiest possible container is not empty. It's a seething ocean of quantum jitter. If you had a detector sensitive enough, you could watch energy flicker into existence and vanish again. Particle-antiparticle pairs popping up and immediately annihilating, all within a time so short that the uncertainty principle permits it. Physicists call these virtual particles, and we'll come back to them later. For now, just know they're there, bubbling constantly in the space inside your sealed box, in the space inside your lungs, in the space between the words on this sentence. You might think this is just a mathematical fiction, a bookkeeping trick in the equations that doesn't correspond to anything real. Physicists thought that too for a while, then they figured out how to test it. In 1948, a Dutch physicist named Hendrik Casimir proposed an experiment that would put two metal plates very close together in a vacuum and watch what happened. If the vacuum really was full of field fluctuations, those fluctuations would press on the plates from the outside. The plates would move. They'd be pushed together by nothing. And they were. Before we step into Casimir's experiment, we need to understand the shaking itself, why a quantum system can never truly be still. Because this jitter is the engine behind everything strange that follows. Picture a child on a swing. You push the swing, it rises, it comes back. Eventually, if you stop pushing, the swing slows down. Friction with the air, friction at the chain, the energy drains away. The swing comes to rest at the bottom, perfectly still. Zero energy. That's classical physics. You can always, in principle, drain a system of all its energy and leave it motionless. The quantum world refuses to let that happen. There's a principle, first written down by Werner Heisenberg in the 1920s, that connects two things you might think have nothing to do with each other: position and momentum, where something is and how fast it's moving. The principle says you can never know both at once with perfect accuracy. Pin down the position exactly, and the momentum becomes completely uncertain. Pin down the momentum exactly, and the position smears out over all of space. Now run this backward. If a particle is sitting perfectly still at the bottom of a well, perfectly still, meaning momentum is exactly zero, then by the principle, its position must be completely unknown. It can't be. We put it in the well. We know where it is, roughly, so its momentum can't be exactly zero. It must be wiggling, at least a little, even at its lowest energy state. This wiggling has a name, zero-point motion. And it's not a theoretical curiosity. We see it. Cool helium gas down as close to absolute zero as you can get. Every other substance freezes solid at some point. Helium refuses. It stays liquid all the way down. Why? Because the atoms are wiggling from zero-point motion, and the wiggling is energetic enough that the atoms can't settle into a crystal. You would need to push harder on the helium, pressurize it, to force the atoms close enough that the solid crystal can form against the jitter. Liquid helium near absolute zero is a substance held in its liquid state by nothing but quantum restlessness. Now take this idea and apply it to a field. A field, remember, has a value at every point in space. That value can oscillate, go up and down, like a wave. Each possible oscillation pattern is like a tiny swing. Each one has its own zero-point motion. Each one is forced by the uncertainty principle to jitter, even at its lowest energy. For a single particle in a well, you get a tiny amount of zero-point energy, manageable, small, no trouble. For a field, you have to count every possible oscillation pattern at every possible wavelength. Waves a mile long, waves a foot long, waves a billionth of a meter long, waves smaller than an atom, waves so small we can't even probe them. Every single one of those wave patterns contributes its own little jitter, its own little piece of zero-point energy. And when you start to add them up, faithfully the way the theory tells you to, you run into something unpleasant. The sum doesn't settle. The shorter the wavelengths you include, the bigger the total gets. Push the calculation to infinitely short wavelengths, and the answer becomes infinite. The vacuum, according to quantum field theory taken at face value, contains infinite energy. That's the first infinity we'll meet. It won't be the last. In fact, the whole history of quantum field theory from the 1940s onward is a history of physicists finding infinities in their equations and inventing increasingly clever ways to subtract them. But here's the thing, that jitter is real. It isn't a bookkeeping fiction. Casimir proposed a way to squeeze it, to force those trembling fields into a narrow space, and watch what happened. Hendrik Casimir was working at the Philips Research Labs in the Netherlands in 1948. He was thinking about a puzzle. Two uncharged metal plates parallel facing each other in a vacuum. According to classical physics, nothing should happen. The plates have no charge. There's no air between them to create pressure. Drop them in empty space, and they should sit there forever, unmoving. Casimir ran the numbers using quantum field theory, and the theory said they will move, slowly, gently, but definitely. They will be pulled toward each other by the vacuum itself. Here's the reason. Picture our earlier idea of the empty box with the photon field jittering inside. The jitter doesn't happen at just one wavelength. It happens at every wavelength, all the way down to the smallest ones the theory allows. Long waves, short waves, everything in between. Now squeeze two metal plates close together. The space between the plates is a kind of cavity, like a pipe organ. An organ pipe can only sustain certain notes, the ones whose wavelengths fit neatly between the ends of the pipe. Waves that are too long to fit simply can't exist inside the pipe. The same thing happens between the plates. The photon field fluctuations that have wavelengths too long to fit between the plates are suppressed. They can't jitter there. But outside the plates, in the open vacuum, no restriction applies. Every wavelength can fluctuate freely. So you have more types of vacuum jitter, pressing on the outside of the plates than on the inside. The imbalance produces a gentle push. The plates feel a force squeezing them together. It's like standing between two walls in a storm. The wind howls on the outside with every gust. Inside, only certain gusts can squeeze through. The difference in pressure pushes the walls inward. Casimir calculated the size of this force. Tiny. For two plates the size of postage stamps held 1/1000th of a millimetre apart, the force is about the weight of a red blood cell, delicate enough that for almost 50 years nobody could reliably measure it. In 1997, a physicist named Steve Lamoureux at Los Alamos finally pulled it off. He used a hypersensitive torsion pendulum and plates coated in gold. He moved them carefully, watched for the slightest deflection, corrected for every stray electric charge and vibration. The signal was there, exactly the size Casimir has predicted 50 years earlier from a theory about the jittering of empty space. Since then, the measurement has been repeated with better and better precision. Different geometries, different materials. Every time the vacuum pushes, every time the numbers match what quantum field theory predicts, not loosely, tightly. Think about what this means. The force that pulls those plates together is not produced by anything you can point to. No air, no charges, no radiation. The force is produced by restrictions on how empty space can jitter. The vacuum has been pressed against itself in a way that creates an imbalance, and the imbalance pushes. We are measuring the energy of nothing. This is the moment when vacuum energy stops being a mathematical curiosity, when the jitter becomes something engineers can exploit. Small devices at the scale of microchips, components packed so tightly their surfaces are micrometers apart, have to be designed with Casimir forces in mind. A satellite's internal mechanisms can stick together from pure vacuum attraction if the designers aren't careful, so the vacuum has energy. We've measured it. But when physicists try to calculate the total, to say how much energy the vacuum actually contains, something spectacularly wrong happens. The number they get is the largest error in the history of science, and to see how we got there, we need to look at the trick physicists invented to handle infinity. Here is the situation quantum field theory left physicists in around 1940. The theory predicts real effects, Casimir's force, the way electrons scatter off each other, the way atoms emit light. In principle, you can calculate these things by adding up contributions from more and more complicated processes, an electron emitting and reabsorbing a single virtual photon, then two, then three, and so on. Each layer of complication adds a small correction to the simple answer. Physicists call these layers loops. There's one problem. When you try to calculate most of these loops honestly, you get infinity. Take a simple question. What is the mass of an electron according to quantum field theory? The theory says, start with the bare mass of the particle, then add the energy of the photon field jittering around it. But the field jitters at every wavelength, and when you include the shortest wavelengths, the correction goes to infinity. The predicted mass of a single electron is infinite. The predicted charge of an electron by the same logic is also infinite. If you were inventing physics from scratch, you'd probably say the theory is broken, throw it out, start over. The physicists in the late 1940s didn't throw it out. They did something strange instead. 3 of them, Richard Feynman in the United States, Julian Schwinger also in the United States, and Shinichiro Tomonaga in Japan, all working independently, discovered that if you were very careful about how you handled those infinities, they could be made to cancel. Here's the rough idea. The bare mass you started with isn't the mass you measure. The measured mass includes all the interactions with the jittering field. So the bare mass must itself be infinite, in just the right way, so that when you subtract it from the total, the leftover is the finite mass you measure in the lab. Infinity minus infinity equals the mass of the electron. This is the move Feynman called hocus-pocus. It feels wrong, it looks wrong, it should be wrong. But when you carry the procedure through for every measurable quantity, mass, charge, magnetic strength, every infinity cancels another infinity, and what's left over is a finite number. And that finite number, checked against experiment, matches reality to stunning precision. The procedure is called renormalization, and for decades it was regarded by many physicists as a practical miracle, a set of rules that worked, even though nobody could fully justify why. Feynman shared the 1965 Nobel Prize with Schwinger and Tomonaga for this work. And in his Nobel lecture and later writings, Feynman was almost openly uncomfortable. He said the procedure was not mathematically legitimate. He said he suspected the theory was wrong at some deep level, and renormalization was a way of hiding the wrongness. He said future physicists might look back and marvel that anyone took such a procedure seriously. But no one could find a better way. Renormalization delivered predictions that matched experiments to a mind-bending accuracy. It worked. And in physics, when something works, people use it. For 40 years, the standard view was that renormalization was a clever trick that somehow gave correct answers for reasons we didn't understand. Then, in the 1970s, an American physicist named Kenneth Wilson came along and completely changed the way everyone thought about it. He gave a deep reason why the infinities appear and why subtracting them works. His answer was both a relief and a warning. The relief: the math makes sense. The warning: it makes sense only because the theory is telling us it doesn't apply at the deepest level. We'll come back to Wilson. For now, know this: every prediction you've ever heard from the standard model of particle physics, every calculation that led to the Higgs boson, every simulation of the Large Hadron Collider, every number that inspired headlines, relies on renormalization. Without this trick, quantum field theory produces only infinities. With it, it produces the most accurate numbers in science. And the first person to point out how strange that is, in public, in writing, was the man who'd helped invent the trick. Richard Feynman won the Nobel Prize in 1965. He was 47 years old, a famous eccentric at the California Institute of Technology, a man who played bongo drums and cracked safes for fun. He'd helped build the atomic bomb at Los Alamos. He'd reformulated quantum mechanics in his late 20s. His diagrams, little sketches of electrons emitting photons, lines meeting at vertices, had become the standard language physicists used to calculate just about everything in the subatomic world. When Feynman said something about quantum field theory, people listened. In his later writing, when he was trying to explain his own theory to general readers, he reached for language that startled his colleagues. He didn't claim quantum electrodynamics was beautiful, or elegant, or clearly correct. He said it was a dippy process. He said he had to resort to hocus-pocus. He wrote that renormalization is what we now call a sweeping under the rug. The exact phrasing varies across his books and lectures, but the sentiment never wavered. What made this so jarring was that Feynman was talking about the most successful theory of his own career, the theory that had won him the Nobel. He wasn't some outsider taking potshots. He was the architect saying openly that he didn't fully trust the building. Some colleagues thought Feynman was being theatrical. He enjoyed provocation. He liked to puncture stuffy academic pretension. Maybe he was overselling his doubts to make a point. But the record shows Feynman said the same things privately to students, in seminars, in letters. He genuinely believed the procedure of renormalization was a stopgap, a technique that got the right numbers out of a theory that wasn't, deep down, quite right. He thought someone eventually would figure out the true underlying structure, and when they did, renormalization would be revealed as a shadow of that deeper principle, the way epicycles in ancient astronomy were shadows of the real geometry of the solar system. Paul Dirac, the British physicist who'd essentially founded quantum field theory in the 1920s, agreed. Dirac lived into the 1980s, long enough to see quantum electrodynamics vindicated by experiment after experiment, and he hated renormalization. He refused, to the end of his life, to accept it as legitimate physics. He wrote that the method was ugly, that it wasn't sensible mathematics, that physicists had merely found a way to sweep the difficulties under the carpet and get on with their calculations. You might think, all right, two old men with aesthetic objections, the predictions work. Who cares if the procedure looks ugly? Here's the trouble. Their complaints weren't merely aesthetic, they were pointing at something specific. Renormalization works by using the measured value of a quantity, the electron's mass, the electron's charge, as an input to fix the infinities. The theory cannot predict those values from first principles, it takes them from experiment. So the theory is not a complete description, it's a framework that, given a few measured constants, can predict everything else to outrageous precision. But the constants themselves are off limits. The theory won't say where they come from. This is the dirty secret of the Standard Model. It contains about 19 parameters, particle masses, coupling strengths, that the theory cannot predict. They have to be measured and plugged in. And then, and only then, does the machine produce correct answers. Feynman suspected this meant the theory wasn't finished, that behind the parameters there was a deeper layer where those numbers would be derivable, not measured. Something simpler, something more honest. We still haven't found it. Meanwhile, the jittering vacuum wasn't just a source of infinities, it was also filled with something very real, fleeting, unmeasurable directly, but leaving fingerprints all over every physical experiment. Go back to the empty box, fields trembling, jitter everywhere. That jitter isn't abstract, it has a shape, and the shape looks a lot like particles. Here's how. In quantum field theory, a steady field at rest corresponds to no particles being present. An excited, wave-like disturbance in the field corresponds to a particle. So whenever a field fluctuates, even briefly, you can think of it as particles flashing into existence for an instant and then vanishing again. These fleeting existences are called virtual particles. The word virtual doesn't mean fake, it means short-lived. Particles that exist only within the time window the uncertainty principle allows, too briefly to be directly caught by any detector. An electron-positron pair might appear, dance around each other for a trillionth of a second, and annihilate back into the vacuum. The same happens for every kind of particle the theory permits. Photons, quarks, even, in principle, heavy things like top quarks and Higgs bosons. The jitter of empty space is, in this picture, a constant seething of particles blinking in and out. Space isn't a stage. Space is a foam. Now, you might reasonably ask, if these things can't be directly detected, how do we know they're there? Maybe they're just a way of talking about the math, a metaphor. The answer is that virtual particles change real measurements, and we've tested this thousands of times to staggering precision. Take a hydrogen atom, one proton, one electron. If you imagine the electron as simply orbiting the proton, you'd predict certain specific energies for the different orbits it can occupy. Physicists made these predictions in the 1930s. Then, in 1947, Willis Lamb measured the energies very carefully, using microwaves to tickle atoms and listen for when they absorbed. He found the energies were slightly off from the simple prediction, not by much, a tiny shift. The shift came to be called the Lamb shift, and when physicists sat down to explain it using quantum field theory, they realized it was produced by virtual photons. The electron in the hydrogen atom is constantly exchanging virtual photons with the proton, constantly absorbing and emitting photons from the vacuum around it. Each of these exchanges subtly kicks the electron, nudging its energy away from the naive prediction. When you sum up all the virtual exchanges, you get exactly the shift Lamb measured. Not approximately, not within a factor of 2. Exactly. This was one of the first confirmations that virtual particles are not a mathematical fiction. They have observable consequences. You can't point to one directly. A virtual photon never reaches a detector, but their collective influence shapes the energies of atoms, the forces between charged particles, the behavior of every experiment we care to run. Here's an image that might help. Think of the electron not as a small clean ball of charge, but as a ball surrounded by a perpetual storm. The storm is made of virtual photons popping out of the vacuum, interacting briefly with the electron, and disappearing. Sometimes a virtual photon creates a virtual electron-positron pair, which exists for a moment before vanishing. Each of these brief guests changes what the central electron looks like to anything approaching from outside. When another particle gets close, it doesn't feel the bare electron. It feels the electron plus its surrounding storm. The effective charge you measure depends on how close you get. Get very close, and you see through the storm to the bare electron, which has a slightly different charge than the one you measure at long distances. This isn't speculation. High-energy accelerators have measured how the electron's effective charge changes with distance. It's a little stronger when you probe at very short distances, exactly the way the storm of virtual particles predicts. And this same storm, when carefully calculated, produces one of the most precise predictions in the history of science. Every electron behaves like a tiny bar magnet. It has a north pole and a south pole. Put it in a magnetic field, and it twists, the way a compass needle twists to face north. The strength of this twist is measured by a number called the electron's magnetic moment. In the 1920s, Paul Dirac wrote down an equation for the electron, the Dirac equation, still a cornerstone of modern physics, and from it he calculated what the magnetic moment should be. The answer came out very clean. If you scaled things properly, the value was exactly 2, not 1.9, not 2.1, 2. For a while, physicists thought this was the end of the story. The electron's magnetic moment is 2. Done. Move on. Then better experiments came along. Physicists built equipment that could measure the moment with growing precision. And the answer wasn't exactly 2. It was 2 plus a tiny bit more. About 0.1% more. Small. but definitely there. This small extra piece is called the anomalous magnetic moment. The word anomalous just means different from the simple prediction, and physicists wondered, where does it come from? Quantum field theory gave the answer. Remember the storm of virtual particles around every electron? Those virtual photons and virtual electron-positron pairs don't just shift the energy. They also change how the electron interacts with magnetic fields. Every virtual exchange adds its own tiny contribution to the magnetic moment. When you add them all up, with the right procedure, using renormalization to tame the infinities, you get a number slightly larger than 2. Julian Schwinger did the first careful calculation in 1948. His answer, 2 plus a piece equal to the fine structure constant divided by twice pi. Numerically, this matched the measurements of his day. The agreement was so good that Schwinger had the formula carved on his tombstone. Since then, the calculation has been pushed further. Physicists have computed contributions from 2 virtual exchanges, then 3, then 4, then 5. Each level is harder. The 5-loop calculation involves thousands of Feynman diagrams, each one a separate integral, some of which take months of supercomputer time. Teams around the world have spent careers on single terms, and the experimentalists have kept pace. The most recent measurements of the electron's magnetic moment come from trapping a single electron in a magnetic field and watching it spin for months, so carefully isolated that even cosmic rays have to be accounted for. The result: the calculation and the measurement agree to 12 decimal places. 12. Let me try once more to give you a feel for that. If you built a fence around the Earth at the equator, 25,000 miles long, and then you predicted its length from theory, 12 decimal places of accuracy would mean your prediction was right to within the width of a few atoms. This is the crown jewel of quantum electrodynamics, the single best confirmed prediction in the history of physics. It's the reason Feynman, even while calling renormalization hocus-pocus, couldn't bring himself to abandon the theory. Something that produces this level of agreement with nature, no matter how ugly the method, has to be telling us something deeply true. The electron passed the test. Every measurement, every calculation, every refinement, all consistent, all tightening, all converging on the same number. But the electron has a heavier cousin, a particle called the muon. Same charge, same spin, same basic properties, just about 200 times heavier. The muon also has an anomalous magnetic moment, and for a few electric years, it looked like the muon was breaking the theory. The muon is, in most respects, a chunky electron. It has the same negative charge, the same spin, the same interactions with every field in the Standard Model. It weighs about 200 times more and it's unstable. A muon in free flight will decay into an electron and 2 neutrinos in about 2 millionths of a second. That's it. Those are the differences. The muon should also have an anomalous magnetic moment. Same story as the electron. The bare value is 2. The storm of virtual particles adds a correction. Quantum field theory can predict the correction. Experimentalists can measure it. The two should agree. There's one reason physicists care more about the muon than the electron: the muon's extra mass. Because the muon is heavier, it interacts more strongly with any heavy, undiscovered particles that might be hiding in the vacuum. The storm of virtual particles around a muon includes every particle that exists, including particles we might not have discovered yet. If there's a new heavy particle out there, it would contribute a slightly larger correction to the muon's magnetic moment than to the electrons. The muon is a more sensitive probe of unknown physics, so physicists have spent decades measuring the muon's magnetic moment with ever-increasing precision. In the 1990s and early 2000s, an experiment at Brookhaven National Lab on Long Island got a result. The number didn't quite match the standard model prediction at the time. The discrepancy was small but persistent. It hovered around the edge of statistical significance for years. Then the experiment moved to Fermilab in Illinois. The giant 50-foot ring that stores the muons was floated on a barge down rivers and around the Florida coast, through Illinois canals to its new home. Physicists rebuilt it, refined it, and started collecting data. The new experiment was called Muon G2. The first results came out in 2021. The discrepancy was still there. The muon's measured moment was slightly larger than the standard model predicted. Not dramatically, a difference in the 6th decimal place. But it was enough that, if the prediction and the measurement were both trustworthy, something was missing from the theory. New particles, new forces, physics beyond the standard model. For 2 years, the physics community buzzed. Papers piled up proposing what the new particles might be. Some proposed new kinds of heavy partners to the electron. Some proposed entirely new forces. Some proposed reviving old ideas that had been gathering dust. The muon, maybe, was about to break the standard model and open the first real door to new physics in half a century. The Fermilab team kept running. More data, more precision. In 2023, they released an updated result. The discrepancy was still there. The measurement was getting sharper. By early 2025, the experimental value was the most precise measurement of the muon's magnetic moment ever made. A measurement accurate to 127 parts per billion, surpassing the experiment's original design goal, Wikipedia. On one side, the measurement solid, getting sharper every year. On the other side, the theoretical prediction, which was turning out to be much more fragile than anyone had realized. The standard model prediction for the muon's magnetic moment isn't one calculation, it's many. The quantum electrodynamic part, virtual photons and electrons, is known to extraordinary precision. But the muon also interacts with quarks and gluons through virtual exchanges, and those calculations are much harder. Quarks don't move freely. They're trapped inside protons and neutrons. Calculating their contribution requires one of 2 approaches. One uses experimental data from other particle collisions. The other uses brute force supercomputer simulations of the quark fields, chopped into grids, a technique called lattice quantum chromodynamics. For years, these 2 methods gave different answers. The data-driven approach predicted a number that disagreed with the Fermilab measurement. The lattice approach predicted a number closer to the measurement. As the lattice calculations improved, something uncomfortable happened. The ground moved under the anomaly's feet. In the spring of 2025, 2 things happened almost in parallel. First, the Muon G2 Theory Initiative, a global collaboration of theoretical physicists whose job is to produce the best possible prediction from the standard model, released a major update. They'd spent years reconciling the 2 competing methods for calculating the hard part of the prediction. The data-driven approach, which had disagreed with experiment, was losing ground. New data from electron-positron collisions, particularly from an experiment in Russia called CMD3, was shifting the data-driven prediction closer to what the lattice calculations had been saying all along. And the lattice calculations were getting better. Supercomputers had grown more powerful. The grids used to simulate quark fields had grown finer. Different independent teams around the world were converging on the same answer. The answer matched the experimental measurement almost perfectly. Then, on June 3, 2025, the Fermilab Muon G2 team announced their final result, incorporating 6 full years of data. The most precise measurement of a muon's magnetic moment ever made. And when compared to the updated theoretical prediction from the lattice calculations, the experimental value differed from the lattice-based prediction by only about 1 standard deviation. Wikipedia. Statistical noise, not a discrepancy, an agreement. The anomaly, the hint of new physics that had driven papers and careers and conference panels for more than 20 years, quietly evaporated. There was no press conference declaring the end. There was no headline. The announcement was technical, careful, hedged. The experimentalists emphasized that their measurement was rock solid. The theorists emphasized that their calculation had genuinely improved. Neither side wanted to say the words, "The anomaly is gone." But reading between the lines, that's what the results said. Think about the emotional arc, just for the physicists. For 20 years, the muon had been the brightest hope for finding physics beyond the standard model. A community had grown around it. Young researchers had written theses. Funding agencies had approved experiments. The muon was the last remaining anomaly at a precision level that couldn't be easily dismissed. It was supposed to be the crack through which new physics would pour. In 2025, the crack sealed up. Not because new physics showed up and filled it, because the crack turned out to have been a mirage, produced by imperfect calculations on the theory side. This is not a comforting story. You might think, great, the standard model works better than we thought. That's good news, right? Here's why it isn't. The standard model cannot be the complete story. We know this for certain. The standard model has no explanation for dark matter. It has no explanation for why there's more matter than antimatter in the universe. It has no explanation for neutrino masses. It has no explanation for dark energy. It has no way to include gravity. The theory is incomplete. Something must replace or extend it. Finding that something requires experiments that reveal a discrepancy, a place where the standard model predicts one thing and nature does another. The muon anomaly was the most promising such discrepancy in a generation, and it just evaporated. Physicists are now left in an uncomfortable position. The standard model, as far as precision tests go, works. It works everywhere we've looked at it, yet we know it cannot be the whole answer. The places where it should be failing, the laboratories and accelerators where new physics should be leaking in, aren't showing anything. The new physics, whatever it is hiding. Some physicists call this the standard model's curse. The theory is too good. It won't yield a clean answer about what comes next. And worse, if you look hard at the theory, really hard, its own internal structure starts to crack open in ways that have nothing to do with new particles, ways that have to do with what the theory actually is. The first crack we'll examine is not in any experiment, it's in the vacuum itself, the empty space we've been peeking at this whole time, the jitter we've been adding up. When you take that adding up seriously and ask, how much energy is the vacuum carrying total? You get an answer that should, by every rule of physics, have destroyed the universe before it was a second old. Here's the calculation that breaks physics. Take the vacuum. All those fields jittering at every wavelength. Each wavelength contributes a tiny amount of energy. Add up the contributions from every wavelength, in every field, and you get a total energy for empty space. This total energy matters because, according to Einstein's theory of gravity, energy pulls on space. Any energy, anywhere, has gravitational effects, mass pulls, light pulls, heat pulls, and vacuum energy should pull too. If the vacuum has a lot of energy, that energy should bend space, stretch it. accelerate the expansion of the universe. The effect of vacuum energy shows up in Einstein's equations as a term called the cosmological constant. Physicists label it with the Greek letter lambda. The cosmological constant measures how much the vacuum is pushing space to expand. Now here's the question. What does quantum field theory predict for lambda? The calculation, in its simplest form, goes like this. You sum the 0-point energies of every mode of every field up to some very high cutoff wavelength. If you cut off at the shortest wavelength, physics can still make sense. Roughly the Planck scale, which is the length below which even our concept of smooth space-time probably breaks down, you get a very specific number. The predicted vacuum energy is enormous. In the units physicists use, about 10 to the 122nd power per cubic meter. That's a 1 followed by 122 zeros, a number so large that writing it out on a line in a book would require more digits than there are atoms in a small galaxy. If the vacuum really carried this much energy, its gravitational effect would have been catastrophic. Space would have torn itself apart in a fraction of a second after the Big Bang. Atoms could not have formed. Galaxies could not exist. You and I, made of matter that needs stable space to hold itself together, would not be here. The universe would be a blur if it existed at all. So the question becomes, what does the vacuum actually carry? What is the real value of the cosmological constant? For decades, physicists assumed it must be exactly zero. Some unknown mechanism must cancel the huge prediction and leave nothing behind. A symmetry, maybe. A hidden principle. Something we hadn't discovered yet which would explain why the vacuum's energy somehow neatly zeroed itself out. Then, in 1998, two independent teams of astronomers, one led by Saul Perlmutter at Berkeley, the other by Brian Schmidt and Adam Rees, were studying distant supernovae. Type 1, a supernovae, which have reliable brightness and work as cosmic distance markers. The teams wanted to measure how the expansion of the universe was slowing down under the pull of gravity. The expansion wasn't slowing down, it was speeding up. The distant supernovae were dimmer than they should have been, meaning they were farther away than expected, meaning the universe had been accelerating, meaning something was pushing space apart. That something, whatever it is, looks almost exactly like a tiny positive cosmological constant. The astronomers could measure its value from the acceleration. The result? Lambda is not zero. It's a small but non-zero positive number. The two teams shared the 2011 Nobel Prize. The picture of a universe accelerated by some kind of dark energy became the standard model of cosmology. And here is where the full horror of the situation reveals itself. The measured value of lambda isn't zero. It's also not the prediction from quantum field theory. It's in between, but very far from both. Let's put the two numbers side by side. The measured value of the vacuum's energy from observations of the accelerating universe is roughly 10 to the negative 9th joules per cubic meter. In more familiar terms, the vacuum of an empty liter carries about as much energy as a single photon of visible light. Tiny, almost negligible. The predicted value from quantum field theory, taken up to the Planck scale, is roughly 10 to the 113th joules per cubic meter. The difference between the two is about 10 to the 122nd, a factor of 1 followed by 122 zeros. Physicists have a word for this. They call it the largest discrepancy between theory and experiment in all of science, and probably the worst theoretical prediction in the history of physics. Wikipedia. To try to make the number human, here's a comparison. Imagine you're asked to predict the weight of a single grain of sand, and your answer, derived from the best theory available, comes out to something heavier than all the matter in a trillion universes combined. That's the scale of the wrongness. No mistake in the history of chemistry, biology, geology, astronomy or engineering comes anywhere close. The worst weather predictions are off by a few percent. The worst economic forecasts are off by factors of 2 or 3. The vacuum catastrophe is off by 1, followed by 122 zeros. And yet this error lives inside a theory that, in other contexts, predicts the electron's magnetic moment correctly to 12 decimal places. What does this mean? One view, the calculation is naive. We shouldn't trust the simple sum of 0-point energies. Maybe most of the contributions cancel, through some symmetry we haven't found, and only a tiny remnant is left. The question is, what's doing the cancelling? For the cancellation to work, it has to happen to one part in 10 to the 122. If even one contribution is off by the tiniest amount, the cancellation fails and the universe blows apart. This is an incomprehensibly fine-tuned balance. Physicists call problems like this fine-tuning problems, and they generally consider them a sign that you're missing something important. Another view, the problem is deeper. Maybe quantum field theory and general relativity simply don't mix well. Maybe there's something fundamentally wrong about how we calculate the energy of the vacuum. The calculation treats the vacuum as a sum of independent oscillators, each one contributing energy to the grand total. Maybe that treatment is wrong. Maybe the vacuum has a structure we don't understand, and the right calculation would give the small measured value naturally, not by cancellation. A third view, some kind of new physics intervenes. Supersymmetry, if it existed, would automatically cancel many of the contributions. Bosonic fields give positive vacuum energy. Fermionic fields give negative vacuum energy. In a perfectly supersymmetric theory, the two cancel exactly. For decades, many physicists bet on this solution. Supersymmetry would explain the vacuum. It would also solve a few other deep problems. It was elegant. It was mathematically natural. And then the Large Hadron Collider switched on. In 2008, it collided protons at energies high enough to produce supersymmetric particles, if they existed. It has been running ever since, with upgrades, with longer runs, with more data. No supersymmetric particle has shown up. Every simpler version of the theory has been ruled out by the experimental absence of its predicted particles. The more baroque versions survive, but only at the cost of giving up the naturalness that made supersymmetry attractive in the first place. The vacuum catastrophe remains unsolved. The worst prediction in physics remains the worst prediction in physics, and nobody knows why the universe isn't shredded. Here's the uncomfortable thing about the vacuum catastrophe that doesn't get enough attention in popular writing. It's not a small mystery waiting to be tidied up. It's a constraint on the structure of reality so tight that reality shouldn't be here. Let me explain. Suppose the vacuum energy really were 10 to the 122nd joules per cubic meter. That's the naive prediction. What would the universe look like? You wouldn't notice it at first. A single cubic meter contains a lot of energy, but it's uniformly distributed. No pressure gradients, no local effects. The vacuum looks the same everywhere. So for a local observer, measuring light in a lab, nothing seems off. The trouble only shows up at cosmic scales. Vacuum energy, remember, pulls on space through general relativity. More specifically, it pushes. A positive cosmological constant makes space expand. The bigger the constant, the faster the expansion. At 10 to the 122nd joules per cubic meter, the expansion rate would be astronomical. Every point in space would be flying apart from every other point with effectively infinite speed. Atoms couldn't hold together. The electromagnetic force that binds electrons to nuclei would lose the race against the expanding distance between them. Nuclei themselves would come apart. Even the strong force, the strongest force in nature, would be overwhelmed. Particles created in the first instant after the Big Bang would be hurled apart before they could find partners to bond with. No hydrogen atoms would form. No light would ever reach anywhere, because the vacuum would carry light's source and target apart faster than the light could cross. The universe would be, within a fraction of a second, a structureless, featureless expansion of isolated quanta. Nothing would cool, nothing would condense, nothing would form. No galaxies, no stars, no planets, no life. The measured cosmological constant, the tiny positive value that's actually driving our universe's gentle acceleration, is just barely large enough to be detected by our most sensitive telescopes. At its measured value, the universe has time, 14 billion years and counting, to form structure, cool gas into stars, forge heavy elements in supernova, seed planets, allow chemistry to happen, allow biology to get started. If the cosmological constant were 100 times bigger, structure wouldn't form. Galaxies couldn't clump out of the primordial soup. The universe would be too diffuse, too quickly, for gravity to pull things together before expansion pulled them apart. So the value we observe isn't just small, it's tuned. It sits at a specific value that permits the existence of everything: atoms, stars, life, while the theoretical prediction, naively, sits 122 orders of magnitude higher than that permissible range. Physicists have a term for this, the fine-tuning problem, and the vacuum energy is its most extreme example. If nature, or some deep physics, is cancelling most of the predicted vacuum energy, it's doing so to an accuracy that no known principle can produce, and the cancellation has to be nearly but not exactly perfect. It has to leave behind just enough residual energy to drive the observed acceleration, but no more. Some physicists have suggested a provocative answer. Maybe there are many universes, each with a different cosmological constant. Most of them collapse or expand too fast for anything interesting to happen in them. We find ourselves in one where the constant happens to be small because no observer could exist in the ones where it wasn't. The multiverse is an answer to the fine-tuning problem. Others reject this as a surrender. It doesn't predict anything. It says, "We got lucky." Physics, they argue, should do better than that. Physics should predict. Nobody has a convincing alternative. The vacuum catastrophe is, as of this moment, an open wound in theoretical physics. We compute a number. It disagrees with reality by 1 followed by 122 zeros. We don't know why. And we don't know what's holding the universe together against our own prediction. The vacuum isn't the only thing that looks impossibly tuned. When we turn to the masses of particles, we find the same ache. The standard model of particle physics contains about 19 parameters that the theory itself cannot predict. Measurement gives their values. Theory uses those values to predict everything else. One of those parameters is the mass of the Higgs boson, the particle discovered at the Large Hadron Collider in 2012. The measured value is about 125 giga-electron-volts. In human terms, roughly 130 times the mass of a proton. Here's the problem. When you calculate using quantum field theory what the Higgs mass should be, you run into the same kind of trouble as with vacuum energy. Virtual particles around the Higgs contribute corrections. every virtual particle, from the electron to the top quark to whatever else exists at high energies, adjusts the Higgs mass through quantum loops. These corrections are enormous. They scale with the square of the energy cutoff you use in the calculation. If you cut off at the Planck scale, the highest energy where our current physics might still make sense, the corrections to the Higgs mass come out to about 10 to the 19th giga-electron-volt squared. That's 17 orders of magnitude larger than the measured Higgs mass squared. For the measured Higgs mass to emerge from this calculation, the bare mass you start with has to cancel the corrections to 1 part in 10 to the 17. A precision cancellation of 17 decimal places, produced by two entirely separate contributions with no known reason to be related. This is called the hierarchy problem. It's another fine-tuning scandal. The Higgs mass sits at a value that, according to the theory, requires a stunning coincidence between the bare mass and the loop corrections. To get a sense of how absurd this is, imagine a pencil balanced on its tip. The tip has to be exactly the right width. Lean even slightly to the left, the pencil falls. Lean slightly right, it falls. The balance has to be maintained to 17 decimal places against constant disturbance. And there's no mechanism keeping it balanced, it just is. Physicists have spent decades trying to find the mechanism. Why would nature choose this finely tuned value when any other value, randomly chosen, would be catastrophic? The most popular answer for 30 years was supersymmetry. Supersymmetry postulated that every known particle has a partner with different spin properties. The contributions from partners would exactly cancel the contributions from original particles. The Higgs mass would naturally sit at a stable low value. The fine-tuning would disappear. Physicists loved supersymmetry. It solved the hierarchy problem. It unified the forces at high energies. It provided candidates for dark matter. It had deep mathematical beauty. By the 1990s, most theorists assumed supersymmetric particles would be found as soon as accelerators got powerful enough. Then the Large Hadron Collider switched on. It was designed, among other purposes, to find supersymmetric particles. Its energy range covered the mass window where the simplest and most elegant versions of supersymmetry predicted partners should appear. The machine ran, and ran, and ran. No supersymmetric particles appeared. Not in 2012, not in 2015, not in 2018, not in later runs. Every time a new experimental result was announced, the allowed mass range for supersymmetric particles got pushed higher. By the mid-2020s, the simplest versions were effectively dead. You could still construct more elaborate theories where the partners hide at higher energies, but doing so reintroduces the fine-tuning it was meant to solve. If the partner particles are heavy, their cancellation against the standard model particles is no longer automatic. It becomes another tuning exercise. The elegance collapses. The hierarchy problem is still here. The Higgs mass still sits at its improbable value, and we have no good explanation for why. It wasn't a bang. It was a long, slow dimming. In the 1980s and 90s, supersymmetry was the default expectation among particle theorists. Textbooks assumed it. Conference talks took it for granted. Graduate students built careers on specific models. The only question was, at what scale will the partners show up? Not, will they show up at all? Then the Large Hadron Collider started collecting data in 2010. Early hopes were high. Rumours circulated in 2011 and 2012 that a signal might be about to emerge, but when the data got properly analysed, there was nothing. The Higgs was found, which was the LHC's signature triumph. Every other search, for squarks, gluinos, neutralinos, the whole zoo of predicted superpartners came back empty. By 2015, the simplest supersymmetric models were excluded. Theorists moved to more complicated versions. By 2020, those were straining under the exclusion limits too. Some theorists proposed that superpartners might sit at energies far above what the LHC could reach, which was allowed technically, but abandoned the original motivation, which was to solve the hierarchy problem at accessible energies. In the hallways of physics departments, the conversation slowly changed, not abruptly. There wasn't a day when someone stood up and declared supersymmetry dead. People just started planning other research programs. Graduate students who'd once flocked to supersymmetric phenomenology drifted to other topics: neutrino physics, dark matter direct detection, machine learning for particle data, anything that wasn't waiting for a superpartner that might never come. Senior theorists who'd built entire careers on supersymmetric models had to decide what to do. Some doubled down, insisting the partners were just heavier than expected. Others quietly shifted their focus. The community didn't hold a funeral, it just stopped planning the wedding. Why does this matter for our story? Because supersymmetry was supposed to be the rescue. It was the natural explanation for why the Higgs mass was small. It was also the natural candidate for solving the vacuum catastrophe, since supersymmetric cancellations would suppress most of the predicted vacuum energy. Without supersymmetry, both problems become orphans. We know the Higgs mass is small, we know the vacuum energy is small, we have no elegant reason for either. The deep conclusion many theorists have drawn is unsettling. Maybe these numbers are simply what they are, and no deep principle determines them. Maybe they're environmental, in the sense that a multiverse of possibilities exists, and we observe the corner where observers can exist. Maybe the clean predictive structure physics aspired to, where every measured quantity could be derived from first principles, is an illusion, and we live in a universe where many parameters are just givens. Or maybe there's still a deeper theory, waiting to be found, that will explain all this in a way no one has thought of yet. Some physicists retain that hope. Others have made peace with the possibility that we've reached a wall. Meanwhile, even in the regions where quantum field theory works perfectly, mathematicians have been pointing at a quiet, embarrassing result. A theorem from 1955 that says, in rough terms, that the way physicists do calculations in quantum field theory can't actually be consistent. It was proved by a Swiss physicist named Rudolf Haag, and most physics students have never heard of it. Rudolf Haag was young when he proved it. Working in Germany and Switzerland in the early 1950s, he was studying the mathematical foundations of the new quantum field theory. And in 1955, he published a result that, taken at face value, was devastating. To understand Haag's theorem, you need one idea. The way physicists calculate almost anything in quantum field theory relies on a trick called the interaction picture. It works like this. You have two theories in your pocket. A simple one where particles don't interact. They just drift around ignoring each other. And the real one, where they do interact. You pretend that at very early and very late times, far from any collision, the particles are essentially free. Between those times, they interact briefly. You calculate the transition between the early free state and the late free state using the interaction as a correction. This is how every scattering calculation you've ever heard of works. Feynman diagrams are a visual shorthand for exactly this procedure. The whole machinery of particle physics predictions, every cross-section, every decay rate, every value computed for the Large Hadron Collider, uses the interaction picture. Haag's theorem says, in essence, that this picture is mathematically inconsistent. Any field that can be related to a free field by the standard transformation used in the interaction picture must itself be a free field, which means the interaction picture cannot represent interacting particles. It's contradictory Wikipedia. Let me put that in plainer language. The textbook method for calculating interactions in quantum field theory, used in every particle physics classroom on Earth, contains a fundamental mathematical contradiction. The procedure assumes something that, by Haag's own proof, cannot be true. And yet the calculations work. This is what physicists live with. Most quantum field theory textbooks aimed at practical applications don't even mention Haag's theorem. They proceed as if the interaction picture is fine, implicitly assuming that someone, somewhere, will eventually find a rigorous framework that justifies what they're doing. Wikipedia. Calculations in specific cases, the way strong force jets spread out, the way particles scatter, give answers that match experiments beautifully. But strictly speaking, according to Haag, those calculations shouldn't be allowed. As one philosopher of physics wrote, Haag's theorem is a valid mathematical result that appears to call into question the foundation of interacting quantum field theory, while the theory itself has proved astonishingly successful when applied to real experiments. Wikipedia. The two statements, both true, sit uncomfortably side by side. Working physicists have several responses. Some dismiss the theorem, arguing that Haag's assumptions are too strict, that real calculations use additional tricks, like cutoffs and regularizations, that sidestep the specific mathematical setup Haag was analyzing. Others concede that Haag is right in the letter of his theorem, but believe the interaction picture is close enough to something rigorous that the practical predictions are still trustworthy. A small minority takes the theorem seriously as a warning that quantum field theory, as currently practiced, is built on sand and needs a full reformulation. Here's what's remarkable. There is no universally accepted resolution. Decades after Haag's proof, the field has not arrived at a consensus on what his result really means. Physicists keep calculating. Mathematicians keep publishing papers, pointing out that the calculations can't really be valid. Both sides are right within their own frames of reference, and the disconnect between them is never quite fixed. This is the quiet scandal of modern physics. Not that our best theory has errors. Errors we could find. Errors we could correct. The scandal is that our best theory is mathematically unsound by the admission of its most careful analysts, and we don't know how to fix it. We just keep using it, because it works, and Haag isn't alone. Other results in the mathematical literature point to similar trouble. Series expansions that don't converge, calculations that diverge at high energies, a millennium problem worth $1 million that asks whether the theory even makes mathematical sense. Each one tells the same story from a different angle. The theory's most honest critics have been saying the same thing, in different ways, for 70 years. The mathematics is broken. The predictions are perfect. Nobody knows why. Walk into any quantum field theory class at any major university. The professor will introduce the interaction picture in the third or fourth lecture. They'll write the equations on the board. They'll show you how to expand the time evolution operator as a series of corrections, each term representing a more complicated interaction. They'll draw Feynman diagrams. They'll calculate a scattering amplitude. What they almost certainly will not do is mention Haag's theorem. This isn't an oversight, it's a choice. And it's made by essentially every physics department in the world. The reasoning goes something like this. Students have limited time. Quantum field theory is already the hardest course in the curriculum. It takes a full year to teach students how to calculate one-loop corrections to simple processes. Teaching them that the procedure they're learning is mathematically inconsistent would only confuse them without adding any practical skill. They need to learn to use the machinery. Questions about the machinery's foundations can wait, maybe forever. So the silence propagates. A graduate student learns quantum field theory from a professor who never mentioned the foundational problems. That student eventually becomes a professor, and they pass along the same curriculum with the same gaps. After a few generations, most working physicists have only the vaguest awareness that their favourite theory rests on unstable ground. There's a useful word for this kind of collective behaviour: compartmentalization. The field compartmentalizes. Calculators calculate. Mathematicians prove theorems. Foundationalists write papers nobody reads. The three groups attend the same conferences but talk about different things. I'm not saying physicists are being dishonest, they're being practical. A working particle physicist has to predict what happens when a proton hits another proton at high energy. That prediction is tested in the next LHC run. If the theory delivers accurate predictions, the theory is useful. The question of whether the theory is rigorously consistent is, from the working physicist's viewpoint, a problem for somebody else. The problem is that somebody else has been working on it for 70 years without solving it. Consider the perspective of a mathematical physicist. They look at the standard particle physics curriculum and they see moves that, by any clean standard, shouldn't be legal. The interaction picture, as Haag showed, can't represent interactions. Renormalization, the trick that tames infinities, relies on subtracting one infinity from another to leave a finite remainder. These procedures aren't shown to be mathematically valid. They're shown to give answers that match experiments. The mathematicians have been pointing out this disconnect since the 1950s. The physicists have a response. It's the standard model works. The predictions are correct to 12 decimal places. Whatever procedure is being used, there must be some rigorous structure it approximates, and that rigorous structure will eventually be found. In the meantime, we have a universe to describe, and we can't wait. This response is reasonable. It might even be right. But it does mean that physicists are using tools they don't fully understand to explore a universe whose laws they're trying to uncover. The tools work. The tool's logic is murky. The results are clear. The justification foggy. Some physicists are more open about this than others. Steven Weinberg, one of the architects of the Standard Model, wrote about the foundational issues with unusual honesty. Kenneth Wilson, who eventually gave renormalization its best defense, did so by reframing what quantum field theory even is. Others prefer to keep their heads down and calculate. Here's the uncomfortable question. If the interaction picture is wrong, and Feynman diagrams are built on the interaction picture, why do Feynman diagrams give right answers? One view, because the theory has enough internal consistency that even incorrect methods, if used carefully, accidentally give right answers. The mathematics is rescuing itself. This is uncomfortable because it sounds like magic. Another view, because the theory we're calculating with is only an approximation to some deeper, truly consistent theory. The approximations happen to preserve the parts of the math we care about, while breaking only the parts we don't notice. A third view, because we've been getting lucky for 70 years, and eventually the luck will run out. Maybe at some new energy scale the theory will catastrophically fail. Maybe we'll find an experimental prediction that it gets spectacularly wrong. Maybe the failure will be the hint we need to find the deeper structure. Nobody knows which view is correct. The silent agreement persists. And behind all of it, waiting in the mathematical literature, is a $1 million problem that no one can solve. In the year 2000, the Clay Mathematics Institute in Cambridge, Massachusetts, announced 7 Millennium Prize problems. Each problem was deemed central to modern mathematics. Each carried a prize of $1 million for anyone who could solve it. 6 of the 7 problems are about topics you'd expect. The Riemann hypothesis, about the distribution of prime numbers. The Navier-Stokes equations, about the motion of fluids. The Poincaré conjecture, about the geometry of 3-dimensional shapes. These are classic, unsolved questions in mathematics. The 7th problem is different. It's a problem in physics. Specifically, it's a problem about quantum field theory. The problem is called Yang-Mills existence and mass gap. It takes its name from a theory written down in 1954 by Chen-Ning Yang and Robert Mills. Their theory generalized the mathematical structure of electromagnetism to situations where the forces involved could be more complicated. It turned out that their idea was crucial. The theory of the strong force, which binds quarks inside protons, called quantum chromodynamics, is a Yang-Mills theory. So is the theory of the weak force, which causes radioactive decay. Most of the standard model is built on Yang-Mills structures. Every year, physicists use these theories to make predictions. They predict how quarks bind, how protons decay, how particles scatter at the LHC. The predictions are tested. The predictions match. All of this is working, has been working for decades. Here's the $1 million question. Does Yang-Mills theory actually exist as a consistent mathematical object? The Clay Institute is not asking whether the predictions work. It's asking whether, if you take the theory seriously as a mathematical structure, you can write down all of its rules precisely and prove that it's self-consistent. Nobody has done this. For any 4-dimensional interacting quantum field theory, including the one that describes the strong force. The mass gap part of the problem asks something specific. Yang-Mills theories predict that the particles that carry the force, the gluons, in quantum chromodynamics, should have 0 mass when written down in their simplest form. But experiments show that the effects of the strong force don't extend to infinity. They have a finite range. Something is giving the force carriers an effective mass. Physicists have understood this effect phenomenologically for 50 years. But proving from the mathematics of the theory that this mass gap exists, proving that it's a rigorous consequence of the equations, has never been done. So here's what the Millennium Problem is really asking. Can you prove that our most successful theory of fundamental physics makes mathematical sense? 26 years have passed. The prize is still unclaimed. Think about what that means. The theory is used every day. Experiments test it constantly. The results match. And yet, as a rigorous mathematical structure, the theory hasn't been proven to exist. Nobody has constructed a fully consistent example of an interacting 4-dimensional quantum field theory. Every attempt so far has either failed or required mathematical tools nobody has developed. Some mathematicians believe the problem is solvable, and we just haven't figured out how. Others suspect the problem might require the invention of entirely new mathematics. A few radical voices suggest that maybe the answer is no. Maybe Yang-Mills theory, as usually defined, doesn't actually exist as a consistent structure, and what physicists have been computing for decades is some kind of approximation to a theory that, taken at face value, would be incoherent. You might think, but if the predictions work, who cares? Call the theory existent by decree. The answers match experiments, so the math must be okay somehow. Here's why that attitude is risky. The predictions work in regimes we've tested: high-energy collisions, nuclear binding, particle decays. We extrapolate the same theory to regimes we haven't tested, to the extremely small distances near the Planck scale, to the interior of black holes, to the first instance after the Big Bang. If the theory isn't rigorously consistent, those extrapolations are built on faith. When a contradiction eventually shows up, we won't know whether it's a hint of new physics or a symptom of the old physics quietly breaking down. The million-dollar problem isn't about intellectual perfectionism. It's about whether we can trust our best theory when we push it to its limits, which is exactly where things get strange. Because when you do push the theory, it starts to break in ways that point to a very old problem. A problem Freeman Dyson noticed in the 1950s and nobody has fully addressed since. Freeman Dyson was 28 years old and working at the Institute for Advanced Study in Princeton. He'd just helped build the formalism of quantum electrodynamics alongside Feynman, Schwinger, and Tominaga. He was one of the young stars of the field. In 1952, Dyson published a short paper that made an argument nobody has been able to refute since. Here's the argument. When physicists calculate anything in quantum electrodynamics, they write it as a series, a sum of terms. The first term is the simplest process. The second term is a small correction from one virtual exchange. The third term is a smaller correction from two virtual exchanges, and so on. The expectation is that each term gets smaller, and the sum converges to a finite answer. Each term in the series is multiplied by a factor of the fine structure constant, roughly 1 divided by 137, small. The theory's accuracy relies on this smallness. You add a few terms, each one 100 times smaller than the last, and you get a stunningly precise answer. Dyson asked a simple question. What if the fine structure constant were negative instead of positive? What would the theory predict? The answer is catastrophic. If the fine structure constant flipped sign, same sign charges would attract each other instead of repelling. Two electrons would pull together instead of pushing apart. Under those conditions, the vacuum itself becomes unstable. Large regions of space would spontaneously create pairs of electrons that attract each other, generating more regions that do the same in a runaway cascade. The whole universe would fall into an unstoppable collapse. So a negative fine structure constant leads to a theory with no stable ground state. The theory isn't physically meaningful. Now the clever part. If the theory with a negative constant is unstable, then the predictions of the real theory, the series expansion in the positive constant, cannot be analytic in the constant. In mathematical terms, this means the series doesn't converge. It can't. Because if it did, you could extend it smoothly to negative values, and you'd be making predictions about a theory that doesn't exist. What this means in practical terms is uncomfortable. The series that physicists use to calculate quantum electrodynamics, the series that gives us the electron's magnetic moment to 12 decimal places, is what mathematicians call a divergent asymptotic series. The early terms get smaller, then, at some point, the terms start getting bigger again. Add too many of them, and the sum runs off to infinity. The early terms give beautiful agreement with experiment. You add 10 terms, the answer matches nature perfectly. Add 100 terms, if you could, which nobody has, and the answer is garbage. Keep adding, and the answer becomes infinite. The theory works not despite being a divergent series, but by stopping at just the right term, before the terms turn around, before the blow-up. How many terms is just the right number? It depends on the calculation, but usually it's at least 100. For our favourite quantity, the electron's magnetic moment, physicists have calculated 5 terms. The 6th would be extraordinarily hard. The 100th is out of reach for the next several centuries of human civilization, even with supercomputers. So in practice, we stop well before the blow-up. But there's a principled question here. The theory doesn't tell us to stop. The theory gives us an infinite series. The mathematicians' theory, the one we're supposed to be using, says add all the terms. Doing that, we now know, gives infinity. So the practice of physics doesn't follow the mathematics of the theory. What we do in real life is a subtle art. We compute a few terms, we check that the terms are shrinking, we stop before they start growing again, and we trust the partial sum. This gives correct predictions. But it's not a rigorous procedure. The theory, honestly applied, gives nonsense. The theory honestly applied up to a certain point gives the best predictions in science. This is the beating heart of what Feynman meant when he called the theory hocus-pocus. The method works, but the method isn't what the theory says to do. And this isn't a quirk of quantum electrodynamics. The same situation holds for every interacting quantum field theory anyone has ever tried to calculate. Quantum chromodynamics, the electroweak theory, every version of the standard model, all of them generate divergent asymptotic series. All of them give correct predictions only when you stop soon enough. Nobody has built a rigorous interacting quantum field theory in 4 dimensions that doesn't have this problem. A theory whose full mathematical content is gibberish, but whose truncated approximations are the most accurate predictions in the history of science. That's what we've got. Quantum chromodynamics is the theory of the strong force, the force that holds quarks together inside protons and neutrons. It's a Yang-Mills theory, so it's one of the ones whose mathematical existence is unproven. It's also the theory responsible for everything that happens inside atomic nuclei. Without it, there's no matter as we know it. And quantum chromodynamics has a strange property that separates it from every other fundamental theory. Nobody has ever observed a free quark. Protons are made of quarks, 3 of them, specifically, 2 up quarks and 1 down quark. These quarks are inside the proton in some sense. They carry charges, they interact through the strong force, they're real. But you can't pull one out. You can't capture a single quark in a lab and study it in isolation. This is called confinement. It says the strong force at long distances gets stronger. Try to pull 2 quarks apart and the force between them grows. Eventually it becomes so strong that it's easier, in terms of energy, to create new quark-antiquark pairs out of the vacuum than to continue separating the original pair. The result is that you end up with 2 protons, or 2 mesons, or 2 of whatever you started with, rather than 1 proton and 1 free quark. Confinement is weird. Every other force we know about gets weaker with distance. Gravity weakens with distance. Electric forces weaken with distance. Even the weak force has a finite range because its carrier particles have mass. The strong force, uniquely, grows with distance until it's essentially infinite. This isn't speculation. It's been observed in countless experiments. Every attempt to produce a free quark has failed. At the Large Hadron Collider, protons are smashed together at energies hundreds of times the proton's rest mass. Quarks are shaken violently loose from their parent protons, and what emerges? Never a free quark. Always jets, collimated sprays of ordinary particles, the debris of the quark's attempt to escape, snapping back into confined structures before it could reach any detector. Here's the problem for theory. Confinement is observed. It has to be true. But nobody has proven, starting from the equations of quantum chromodynamics, that confinement happens. The proof would require showing that the theory, in its low-energy behavior, inevitably produces this behavior. It would require understanding the theory in the regime where perturbation theory fails, where the coupling is strong, where the series doesn't work, where Feynman diagrams proliferate beyond any hope of summation. We don't have this proof. We have strong numerical evidence from lattice calculations, which we'll discuss in a moment. We have arguments based on analogies to other systems. We have experimental observations, but we don't have a mathematical derivation starting from first principles. This is the hardest part of the millennium problem. The mass gap that Yang-Mills theory is supposed to have is closely related to confinement. If you could prove the mass gap rigorously, you'd probably be very close to proving confinement. Neither has been done. Meanwhile, quantum chromodynamics is the theory we rely on whenever we talk about the inside of protons, nuclear reactions, the formation of matter in the early universe, or the structure of neutron stars. The theory works. The predictions are tested. The math, in the regime where it matters most, where the coupling is strong and the quarks abound, we can't do analytically, we can only simulate. And the simulations themselves are a confession of how incomplete our understanding is. A brute force approximation of a theory we can't handle with pencil and paper. If you can't solve quantum chromodynamics with equations, you can try to solve it with a computer. This is what physicists have been doing since the 1970s, and the approach has a name: lattice quantum chromodynamics. The idea is straightforward in principle. The theory is defined on continuous spacetime, smooth with an infinite number of points. Computers don't handle infinity well, so you replace continuous spacetime with a grid, a three-dimensional lattice of points, spaced some distance apart, stretching across a finite volume. Instead of fields that vary smoothly everywhere, you have field values defined at each lattice site, and rules for how the values at neighbouring sites are related. On this grid, you can compute things. You can set up initial configurations of quark and gluon fields. You can evolve them according to the rules of the theory. You can measure what the theory predicts in the limited region of the grid. The calculations are brutal. A realistic simulation of a proton on a lattice, fine enough to capture the relevant physics, requires enormous amounts of computer time. The grids have billions of points. The evolution steps number in the millions. Supercomputer centers are dedicated almost entirely to lattice calculations. The world's most powerful machines are running quantum chromodynamic simulations around the clock on every continent. The payoff is real. Lattice calculations have successfully computed the masses of protons, neutrons, and other particles made of quarks, starting from just the parameters of the theory. The predictions match the measured masses to a few percent. For comparison, that's a calculation done essentially from scratch. Given just the quark masses and the strength of the strong force, the computer tells you what hadrons should weigh. The answers agree with reality. Lattice calculations have also been crucial in the muon G2 story. The hardest part of predicting the muon's magnetic moment involved contributions from virtual quark-antiquark pairs, and those contributions could only be reliably computed on lattices. The improved precision of lattice calculations is exactly what allowed theorists to close the muon anomaly in 2025. But here's the uncomfortable thing. Lattice quantum chromodynamics is not quantum chromodynamics, it's an approximation. By introducing a discrete lattice, we've changed the theory. The original theory is defined on continuous spacetime. The lattice theory lives on a grid. The two are related by a limit. If you make the grid finer and finer, the lattice theory should approach the continuum theory. But nobody has proven that this limit exists in a mathematically rigorous sense. You can take finer and finer grids, and the results seem to stabilize. They converge to numbers that match experiment. But converging numerically is not the same as a mathematically rigorous limit. The question of whether the continuous theory actually exists, the question the Clay Institute is asking, isn't answered by lattice calculations. In practice, physicists treat lattice calculations as the closest thing to a rigorous definition of quantum chromodynamics we have. In a sense, lattice theory is the theory. The continuous version is an idealization that may or may not make sense, but the lattice version, for any finite grid, is a well-defined computer program. This is a remarkable retreat from the ambitions of mid-20th century physics. The original hope was that quantum field theory would be a beautiful, rigorous mathematical structure, something like classical electromagnetism, but deeper. What we actually use is a brute force approximation on a computer grid. It works, it gives right answers. But if you ask what the theory really is, at the deepest level, the honest answer is it's whatever the computer spits out, and computers have limits. There are regimes lattice calculations can't handle. Very low energy physics where the grids would need to be enormous. Physics involving dynamical quarks in certain chemical states, where technical obstacles called the sign problem make the calculation impossible to perform efficiently. The lattice saves us in many cases, not all. Which means that even our computational replacement for the theory leaves parts of nature beyond our reach. And those parts include some of the most fundamental properties of matter. Lev Landau was a Soviet physicist working in the 1950s. One of the great minds of 20th century physics, the winner of the Nobel Prize in 1962, and a man famous for his sharp tongue. He was studying the behavior of electrons at extremely short distances using the tools of quantum field theory, and he found something that troubled him. Remember the idea that a bare electron sits inside a storm of virtual particles. The virtual particles polarize the vacuum around the electron, partially cancelling its bare charge. When you measure the electron from far away, you see the bare charge plus the shielding effect, reduced compared to what the bare charge really is. Landau asked, what happens if you probe closer and closer? As you get nearer to the electron, you see through more of the shielding. The effective charge you measure grows. At very short distances, the charge should be very large. Landau pushed the calculation further. Using quantum electrodynamics, he asked how the charge changes as a function of distance. The answer was a specific mathematical formula, and the formula had a striking feature. At some extremely short distance, absurdly short, many orders of magnitude smaller than the size of a proton, the formula predicts that the charge becomes infinite. This point is called the Landau pole. At the Landau pole, the theory breaks down. It predicts infinite charge, which doesn't make physical sense. At energies or distances beyond this point, quantum electrodynamics, taken at face value, is incoherent. You might say, alright, so the theory breaks down somewhere far beyond experimental reach. Why should we care? Here's why. If a theory breaks down at high energies, it's a sign that the theory isn't fundamental. It's a sign that the theory is only an effective description, valid up to some energy scale, above which it needs to be replaced by something deeper. For quantum electrodynamics, the Landau pole is at energies so absurdly high that it's not a practical problem. The theory works perfectly in every regime we can test. By the time you'd reach the Landau pole, quantum electrodynamics is already merged into the broader electroweak theory, and eventually, presumably, into something we haven't discovered yet. So the pole is a sign that the theory isn't ultimate, not a crisis in its predictions. but the Landau pole has a deeper implication. Some theorists have argued that if you take quantum electrodynamics seriously as a standalone theory, the only way to avoid the pole is if the theory is trivial, meaning the charge of the electron is exactly zero at all distances. In other words, the only rigorous interacting version of quantum electrodynamics is one where there's no interaction at all. This is called the triviality problem, and it's genuinely unsettling. If it's true, then quantum electrodynamics, as a fundamental theory by itself, simply doesn't exist as a consistent mathematical object. What we compute with every day is either an approximation to something bigger or a structure that only makes sense when cut off at some finite energy. Lattice simulations of simple quantum field theories have supported the triviality argument in some cases. For instance, a simpler theory called phi-4, often used as a toy model, shows triviality in 4 dimensions. Make the simulation larger and larger, and the effective coupling goes to 0. The only rigorously defined version of phi-4 theory in 4 dimensions is one where the particles don't interact. If this is true of quantum electrodynamics, we face a strange situation. Our most precisely tested theory, the one that predicts the electron's magnetic moment to 12 decimal places, may be mathematically non-existent as a standalone fundamental theory. What we're computing is a calculation within an approximation that only makes sense in a limited energy range, inherited from a bigger theory whose structure we don't fully understand. This is the situation. Our best fundamental theory, when pressed hard enough, eats itself. The Landau pole is the bite mark. Up to this point, we've been talking about the vacuum as if there's just one, the empty state, the lowest energy configuration, a definite thing you could, in principle, point to. It turns out quantum field theory doesn't have just one vacuum. It has an uncountable infinity of them, and which one you're working in determines everything about the physics you compute. Let me unpack this. In the early chapters, I described the vacuum as the state where no particles are present, and fields jitter at their minimum level. This is the simplest picture. It works well for free field theories, where the particles don't interact. For those theories, there's a unique vacuum, a single lowest energy state called the Fock vacuum, and particles are excitations above it. For interacting theories, the ones that describe reality, things are different. Mathematicians have shown that interacting quantum field theories generally have what are called inequivalent representations. This means you can build the theory starting from different vacuum states, and these different starting points lead to different predictions for local properties. A particle in one vacuum doesn't even correspond to the same kind of object as a particle in a different vacuum. Worse, there's no obvious rule for picking the right vacuum. The theory itself doesn't tell you which vacuum to use. Physicists typically choose one by convention, the one that's stable against small perturbations, or the one that matches observational data. But the choice is something that has to be imposed from outside. This is related to Haag's theorem. One of the consequences of Haag's proof is that the free vacuum, used in the interaction picture, is not the same as the true vacuum of the interacting theory. They live in different representation spaces. The practice of building interacting theory on top of free theory foundations is unjustified at a deep mathematical level. The vacuum structure problem has physical consequences in situations where multiple stable vacua actually exist. The most famous example is the Higgs field. The standard model predicts that the Higgs field has potentially more than one stable value. We live in one of them, the value that gave us the particle masses we observe. But there might be other possible values, lower in energy, deeper wells in the field's potential, that the universe could have settled into, or could still settle into. Calculations suggest that our Higgs vacuum might be metastable, stable against small disturbances but not the absolute lowest energy state. Given enough time or a big enough fluctuation, our vacuum could transition to a lower one. The transition would be catastrophic. The particle masses would change. The chemistry that makes life possible would be rewritten. Everything we know would be swept away in a wave of vacuum decay that expands outward from the nucleation point at close to the speed of light. When physicists calculate the lifetime of our vacuum, they get numbers that are reassuring. The expected decay time is much longer than the current age of the universe. We're not about to spontaneously combust. But the calculation depends on assumptions about the standard model at energies we've never tested. If new physics enters at higher energies, the vacuum stability could be very different from what the simple calculation suggests. This isn't just an abstract curiosity. The fact that multiple vacua exist, that we don't have a principled way to choose between them, that our universe happens to live in one that's stable enough to have galaxies and life. This is another fine-tuning problem, another coincidence without explanation. Another place where the theory tells us a story we can't fully understand. So when we say the vacuum jitters, it's worth asking, which vacuum? The answer, properly stated, is the one we happen to live in for reasons we don't know, which might change at any moment for reasons we don't understand, and which might not be the unique natural choice of the theory we think we're using. The story so far has been bleak. Renormalization looks like a trick. Feynman diagrams rest on a broken foundation. The series diverge. The Landau pole threatens. The vacuum isn't unique. The math is shaky. And yet the predictions work. Why? In the 1970s, an American physicist named Kenneth Wilson gave an answer that changed everything about how physicists think about quantum field theory. He won the 1982 Nobel Prize for it. And his answer is still the closest thing we have to a justification for why our calculations make sense. Wilson's idea came from thinking about a different problem entirely. He was studying phase transitions, the moments when water freezes, or when a magnet loses its magnetism, or when a liquid boils. These systems have a property called criticality. At the exact temperature where the transition happens, the system shows fluctuations at every length, scale, simultaneously. Clusters of aligned spins within clusters, fractally self-similar, spanning from the microscopic to the visible. Wilson developed a mathematical technique for handling these situations. He called it the renormalization group. The idea is to treat physics at different length scales as different theories, and to track how the theory at one scale is related to the theory at a bigger scale. Think of it as zooming out. When you look at a rough surface up close, you see every bump. When you step back, the bumps average out, and the surface looks smooth. Wilson showed how to systematically extract the smooth, larger scale description from the bumpy, smaller scale one. When he applied these ideas to quantum field theory, something beautiful happened. The infinities that had plagued the theory for decades stopped looking like bugs. They started looking like features. Here's Wilson's insight. Quantum field theory, as traditionally written, is an attempt to describe physics at arbitrarily short distances. You include fluctuations at every wavelength down to zero. That's where the infinities come from. But maybe that ambition was wrong. Maybe, Wilson said, we should think of quantum field theory as only valid up to some maximum energy. Above that energy, the theory is replaced by something else, some deeper theory that we might not know yet. If you define the theory with a cutoff, only include wavelengths longer than some minimum. Everything is finite. No infinities. The calculations are well defined. And here's the magic. When you then study how predictions change as you shift the cutoff to different energies, you find that most details of what's happening at the smallest scales simply don't matter for observations at low energies. They're averaged out, washed away. The low-energy physics is governed by a small number of parameters that survive the zooming out process. This is why renormalization works. When you renormalize a theory, you're really just adjusting a few parameters to account for the effects of the physics you haven't specified at high energies. The procedure isn't a trick. It's the correct way to build a theory when you don't know what happens at the deeper scales. This framework is called effective field theory. And it's not just a justification for old procedures, it's a shift in philosophy. Wilson was saying, stop trying to write down theories that describe everything at every scale. Instead, write down theories that describe what you can observe, given what you currently know. Your theory is an effective description of nature, valid within some range of energies, ignorant of what lies above it. This is a dramatic admission. For 300 years, physics had been about finding the ultimate laws of nature. The true equations, valid at all scales, complete. Wilson was saying that maybe there are no ultimate laws accessible to us. Maybe there's only a tower of descriptions, each valid in its own regime, each replaced by a deeper theory at higher energies, each one effective rather than fundamental. The vacuum catastrophe, in this light, looks a little different. It's not that the theory is catastrophically wrong. It's that we're extrapolating the theory beyond its domain of validity. The naive calculation assumes the theory applies all the way up to the Planck scale, summing fluctuations at every wavelength down to incredibly short ones. But maybe the theory shouldn't be trusted that far. Maybe at some high energy, new physics takes over, and the contributions to the vacuum energy from above that scale are governed by rules we haven't discovered. If the cutoff is at a low enough scale, the predicted vacuum energy becomes much closer to the observed value. The catastrophe is reduced, not eliminated. Even with modern cutoffs, the prediction is still off by many orders of magnitude, but the discrepancy becomes a puzzle rather than a disaster. This is the modern view. Quantum field theory isn't a fundamental description of nature. It's an effective description, valid up to some scale, built on foundations we don't yet see. Wilson's insight saved quantum field theory from conceptual collapse, but it also changed what physicists think they're doing. Before Wilson, quantum field theory was supposed to be the description of fundamental matter, the true equations, the final word, modulo some technical work to be cleaned up later. After Wilson, quantum field theory became a framework for writing effective descriptions of nature at whatever energy scale you're interested in. You want to describe low-energy nuclear physics? Write an effective theory of protons and neutrons. Forget about quarks. They're inside the protons, their effects are absorbed into the parameters of the effective theory. You want to describe higher energies? Switch to quantum chromodynamics, where quarks and gluons are the relevant degrees of freedom. Go higher, the electroweak theory unifies electromagnetism with the weak force. Higher still, grand unified theories, speculative extensions, things we don't really know. Each theory in this tower is valid up to some scale. Each one is an effective description, replaced by the next at higher energies. None of them is the last word. This has a strange implication. If every quantum field theory is an effective description, then maybe there is no fundamental theory. Maybe the tower goes all the way up forever, each theory replaced by a deeper one, with no bottom. Or maybe it ends at some point, and maybe string theory or loop quantum gravity or something we haven't dreamed of is the final layer. We don't know. We have no experimental way to check. What effective field theory gives up is the dream of explanation from first principles. The parameters of each theory, particle masses, coupling constants, are inherited from the theory one layer deeper. If you want to explain why the electron's mass is what it is, you need to understand the theory at the next layer up. If that theory also has unexplained parameters, you need to go further. If there is no bottom, you never reach an explanation. Parameters are just what they are. Some physicists find this freeing. It means you don't have to solve everything at once. Pick an energy scale. Write down the relevant degrees of freedom, calculate. The deep questions can be left for later. The effective theory is what it is, valid where it's valid, silent about what it can't see. Others find it despairing. It feels like an abdication. Physics was supposed to penetrate to the fundamental layer. Now we're told there might not be a fundamental layer, and even if there is, our current tools can't reach it. Here's the practical consequence. Effective field theory explains why renormalization works. The parameters we measure are just the parameters of the current effective theory, which absorb whatever is happening at higher energies. The infinities of the old perturbative approach were a sign that we were trying to extrapolate beyond the theory's domain. Taking effective field theory seriously, the infinities disappear. They were never real. They were an artifact of pretending we knew more than we did. But effective field theory does not answer all the foundational questions. It doesn't tell us whether any specific theory, Yang-Mills, quantum electrodynamics, the full standard model, is rigorously consistent at any energy scale. It tells us how to think about the tower of theories, but it doesn't complete the tower. The Clay Millennium problem remains open. Hagg's theorem remains valid. The series still diverge. The Landau pole still looms. What Wilson gave us is a way to live with the trouble, a way to interpret what we're doing so that it makes sense, not a proof that everything is fine. A useful philosophical stance that makes the calculations sensible to us, and that maybe is the deepest panic. Not that quantum field theory is wrong, not that we have to throw it out, but that the best we can say about our most successful theory is that it's an effective description of something deeper we've never seen, whose existence we've never proven, whose structure we can barely guess at. Here's a question that sounds trivial but isn't. When a detector clicks in a particle physics experiment, what is it detecting? The intuitive answer is a particle, an electron, a photon, a muon. The detector registers the arrival of a localized object. The theoretical answer is a complicated interaction between the field being measured, the apparatus, and the vacuum. What's detected isn't really a particle. It's an event in the field that the detector interprets as particle-like, through processes that themselves are built on the theory we're trying to test. Think of it this way. An electron, in quantum field theory, is a specific kind of disturbance in the electron field. The detector, made of atoms, is a collection of other fields. Electron fields, photon fields, quark fields, all coupled together. When the electron disturbance arrives at the detector, it interacts with these fields, and something happens. A voltage pulse, an ionization, a track in a bubble chamber. That something is what gets recorded. The particle is inferred from the recording. This matters because the concept of a particle in quantum field theory is less solid than textbook descriptions suggest. In some situations, there isn't even a well-defined notion of particle. Near a black hole's event horizon, two different observers, one falling in, one hovering at a distance, disagree about whether the vacuum contains particles at all. This is called the Unruh effect. An accelerating observer, moving through what an inertial observer calls empty space, will see themselves surrounded by thermal radiation. Particles are observer-dependent. In curved space-time, things are worse. The concept of a particle is tied to the concept of a preferred reference frame. In general, curved spacetimes don't have preferred frames, and the particle concept becomes ambiguous. What one observer calls a vacuum, another calls a thermal bath. Both can be correct in their own frames. This ambiguity extends to practical experiments. The particles produced in a high-energy collision aren't really well defined until they're far from the collision point, moving freely toward detectors. Close to the interaction, the concept of a single particle doesn't apply. The fields are all tangled together, only asymptotically, in the limit where time goes to infinity and the collision products separate to large distances, can physicists sensibly speak of definite particles with definite momenta. This is the procedure called asymptotic scattering. You treat the initial state as free particles coming in from infinity, and the final state as free particles going out to infinity, and you calculate the transition amplitude between them. Every particle physics prediction is an asymptotic scattering amplitude. What happens in between, the actual interaction, isn't described by any clean particle picture. It's a mess of interacting fields, and the particle concept only makes sense before and after. So every measurement in particle physics is technically an asymptotic measurement. You never directly observe the interaction. You observe what comes out of it, far from the collision point, after the fields have untangled into independent excitations that can be called particles. This works, mostly. Detectors are far from collision points. Asymptotic particles are what we see. But the foundational issue is real. The theory's predictions are for asymptotic states, and the only reason this is adequate is that our instruments happen to be far enough away to count as asymptotic. If we could probe the inside of an interaction directly, we wouldn't know what we were measuring. And even this asymptotic scattering framework depends on Haig's theorem being ignored. The S-matrix formalism that describes scattering assumes that you can relate free states far away to interacting dynamics in the middle. That's exactly the kind of move Haig's theorem says shouldn't work. We do it anyway, every day. The results match experiments to remarkable precision. The conceptual bookkeeping doesn't add up. Here's something we haven't discussed yet. The standard model contains not one set of matter particles, but three. Our familiar matter, the stuff you're made of, the stuff the Earth is made of, consists of electrons, up quarks, and down quarks, plus some neutrinos to make the numbers work out. These four particles, together with their force carrier companions, are enough to build atoms, molecules, rocks, water, and living things. But the standard model predicts, and experiments confirm, that these particles have heavier siblings. Two more generations of them. The electron has a cousin called the muon, which is about 200 times heavier. The muon has a cousin called the tau, which is about 17 times heavier still. The up and down quarks have heavier counterparts too, the charm and strange, and the top and bottom. 3 generations, identical in every respect. Same charges, same spins, same force interactions, except for mass. The second and third generations are heavier than the first. The top quark is the heaviest of all, roughly as massive as a gold atom, despite being a single fundamental particle. Why 3? The standard model has no explanation. The theory takes the existence of 3 generations as an input, not a prediction. The masses of the heavy particles are parameters, numbers measured in experiments, plugged into the equations, accepted without derivation. This is another unexplained fact, and it's a deep one. If the universe only contained the first generation, every observable property of matter would be essentially the same. Atoms would look the same, chemistry would work. The strong force would bind protons and neutrons, stars would shine, planets would form, life could happen. These second and third generations seem to be surplus to the basic requirements of existence. So why do they exist? And why exactly 3? For decades, physicists looked for hints. Maybe the pattern of generation masses follows some simple formula. Maybe there's a hidden symmetry that forces exactly 3. Maybe there's a principle that explains the strange ratios of masses. No convincing answer has emerged. Various ideas have been proposed and tested. Most have been ruled out. The ones that survive are baroque. They assume new structures, new particles, new symmetries, none of which have been observed. There's a principle in physics that goes back to the 19th century. Anything not forbidden is compulsory. If the laws of physics don't prohibit some phenomenon, nature tends to realize it. 3 generations exist, perhaps, because nothing in the theory forbids them. They just appear, with the masses they have, because that's how the theory works. This is a deeply unsatisfying answer. Physicists want explanation, not tolerance. The existence of 3 generations is a data point that seems to demand a theory behind it. That theory hasn't been found. Worse, the heavy particles raise the hierarchy problem to an even sharper level. If there are 3 generations with wildly different masses, what sets the scale of those masses? The top quark is about 100,000 times heavier than the up quark. The tau is about 3,000 times heavier than the electron. Why these ratios? Why not 1s, or 10 times differences, or a simple arithmetic progression? Every attempt to find a pattern has failed. The mass ratios are, as far as we can tell, arbitrary. The standard model takes them as inputs. No deeper theory has explained them, and the neutrinos, the lightest of the matter particles, add their own mystery. We know they have small but non-zero masses, measured through a subtle quantum phenomenon called oscillation, where one flavor of neutrino transforms into another as it travels. But the standard model, in its original form, predicted neutrinos to be massless. The masses had to be added by hand, through extensions to the theory that nobody has rigorously tested. The generation structure is one more unexplained pattern in a theory that predicts everything except the things we'd most like to predict. Inside quantum chromodynamics, the theory of the strong force, there's a parameter that should naturally be large and isn't. Let me explain. Quantum chromodynamics has a mathematical parameter, usually called theta, that controls a particular kind of symmetry violation. Specifically, it controls whether the strong force treats particles and antiparticles slightly differently when you reverse time. In most of physics, particle-antiparticle symmetry is slightly broken. The weak force, responsible for radioactive decay, is famously asymmetric. It treats left-handed and right-handed particles differently. Experiments have measured violations of combined charge and parity symmetry, the so-called CP violation, in weak processes. These violations are tiny but real, and they're probably responsible for the fact that we have a universe made of matter rather than a universe of pure radiation. The strong force, according to theory, should have a similar asymmetry. The parameter theta, if non-zero, would produce observable effects. Specifically, it would give particles called neutrons a slight electric dipole moment, a preferred electrical direction that should be measurable. Experiments have looked for this effect with exquisite precision. The results show that theta must be extremely small. The current experimental limits place it at less than about 10 to the negative 10. In practical terms, theta is indistinguishable from zero. Here's the problem. There's no reason within the theory for theta to be small. It could be anything. A parameter ranging from 0 to 2 times pi is natural. All values are equally reasonable from the theory's perspective. A value of 10 to the negative 10 is exquisitely tuned. For theta to sit at this value, some mechanism must be pushing it there, and the standard model contains no such mechanism. This is called the strong CP problem, and it's another fine-tuning problem, another parameter whose value in the universe is hard to explain without invoking some special mechanism that nobody has confirmed. The most popular proposed solution from the 1970s invokes a new particle called the axion. The axion is a hypothetical particle that couples to theta in a specific way and dynamically drives it to zero. If axions exist, they would naturally solve the strong CP problem, and they would also be candidates for dark matter, which we know must exist but haven't identified. Experiments have been searching for axions for decades. The most sensitive detectors look for axion photon conversions in strong magnetic fields, or for oscillations in atomic systems that would be affected by passing axion dark matter. Nothing definitive has been found yet. There are tantalizing hints from some experiments, but nothing that rises to the level of discovery. If axions don't exist, we're back to the fine-tuning puzzle. Why is theta so small? Maybe there's a different mechanism nobody has thought of. Maybe it's another case where the universe just happens to sit at a favourable value, because observers could only exist in universes with small theta. Maybe we're missing something fundamental about how the strong force works. Stack this on top of everything else. The cosmological constant is fine-tuned, the Higgs mass is fine-tuned, the vacuum stability is fine-tuned, the theta parameter is fine-tuned. The standard model contains several places where parameters sit at unnatural small values, with no principled reason. The theory doesn't explain why. It simply accepts that nature has made specific choices that allow our universe to exist. Is this a clue to deeper physics? Or is it a brute fact that we have to live with? The disagreement among physicists on this question runs deep. Some are optimistic that deeper principles will be found. Others have concluded that the universe is in some ways genuinely arbitrary, and physics has reached the limit of what derivation from first principles can accomplish. Every problem we've discussed so far is a problem within quantum field theory. The vacuum catastrophe, the hierarchy problem, the series divergence, the mathematical issues, all of them show up inside the framework of fields and particles. But there's one force we haven't discussed, the oldest force humans ever discovered, the force that keeps us on the ground, keeps the Earth in orbit, keeps galaxies together, gravity. Gravity in Einstein's general relativity isn't a force like the others, it's the curvature of space-time itself. Massive objects bend space, and other objects move along the bent geometry. The theory is beautiful, predictive, tested to extraordinary precision. Gravitational waves, predicted by Einstein in 1916, were directly detected by LIGO in 2015. The problem is that general relativity is a classical theory. It doesn't fit into the framework of quantum field theory. And every attempt to quantize it, to treat gravity as a quantum field like the others, has failed. Here's why. When you try to apply the usual recipe of quantum field theory to the gravitational field, you run into infinities that can't be tamed. The standard model's infinities are controllable through renormalization. gravity's infinities aren't. Every attempt to calculate a gravitational process using quantum field theory techniques produces an infinite sequence of worse and worse divergences. No finite set of parameters can absorb them. The theory, in the technical sense, is non-renormalizable. This means quantum gravity, treated naively, cannot make predictions. At any energy scale, you'd need infinitely many parameters to specify the theory. Since you can't measure infinitely many parameters, you can't make calculations. There are ways around this. Effective field theory applied to gravity gives a theory that's usable at low energies. You can compute gravitational effects in regimes where quantum corrections are small. But at high energies, near the Planck scale, where quantum effects become important, the effective theory breaks down, and we don't know what replaces it. String theory was one proposal for a replacement. Loop quantum gravity was another. Neither has produced unambiguous experimental predictions. String theory, in particular, has been accused of being untestable, producing frameworks so flexible that they can accommodate almost any observation. The field has been arguing about this for 40 years. The upshot is that quantum field theory, as we have it, is not a complete framework. It doesn't include gravity. Any extension that does include gravity requires either new mathematical structures we don't fully have, or entire new physics we haven't discovered. This is deeply connected to the other problems. The cosmological constant, for instance, is a gravitational phenomenon. It's how vacuum energy couples to the geometry of space-time. The fact that our calculations of vacuum energy go so horribly wrong is a hint that we don't understand how quantum fields couple to gravity. Maybe the solution to the vacuum catastrophe requires quantum gravity. Maybe the solution to quantum gravity requires understanding the vacuum. The two problems might be one problem, seen from different angles, but as of right now we don't have either solution. Gravity remains outside the quantum field theoretic framework, untamed, quietly mocking our best theoretical machinery. When physicists talk about the Standard Model, they're talking about 3 of the 4 known forces. Gravity is conspicuously absent, not because we don't care, but because we don't know how. The absence of quantum gravity is probably the deepest unresolved issue in physics, and any replacement for quantum field theory, anything that eventually solves the mathematical problems we've been discussing, will probably have to include gravity as an essential part. The old approach of handling the Standard Model first and adding gravity later has produced decades of frustration and no results. The solutions, if they come, will likely involve rethinking the whole framework, which is roughly where some theoretical physicists are now. Not calculating, not proving theorems. Sitting quietly, staring at blackboards, trying to figure out how to start over. If the Standard Model is incomplete, and we know it's incomplete, then something must be hiding. New particles, new forces, new structures, physics beyond the Standard Model, waiting to be discovered. For 50 years, this was the working assumption of particle physics. Build bigger accelerators, push to higher energies, find the new stuff that completes the picture. Accelerators got bigger, energies went up. The Tevatron, the Large Electron-Positron Collider, the Large Hadron Collider, each generation reaching further than the last. The Standard Model particles that had been predicted were all found. The W and Z bosons, the top quark, finally the Higgs in 2012. And the new physics beyond the Standard Model? Nothing. No supersymmetric partners, no extra dimensions, no dark matter candidates in the expected mass ranges, no exotic heavy particles. Every search has come back empty. Some physicists call this the nightmare scenario. The standard model is complete at accessible energies, but we know it's not fundamental, and nothing new shows up to point us beyond it. We're stuck. There's a useful analogy. Fermi's paradox from astronomy asks, where are the aliens? If life is common in the universe, why haven't we detected any evidence of technological civilizations? The particle physics version is similar. If new physics exists, why haven't accelerators found it? Possible answers, in both cases, are varied and speculative. Maybe the new particles exist at energies far above what our accelerators can reach. Maybe the relevant phenomena happen in environments we don't probe. Very early universe, black hole interiors, places no experiment can access. Maybe the standard model is a better approximation to the full theory than anyone expected, and the real physics is buried deep in a regime we'll never touch directly. Maybe the nature of fundamental physics is such that there isn't a clean next layer. Maybe what's above the standard model isn't a slightly bigger theory with a few more particles, but a fundamentally different framework where the concept of a particle itself breaks down. In that case, our experiments built to find new particles would find nothing because there are no particles to find. We'd need to ask entirely different questions. This is a serious possibility being discussed seriously by theoretical physicists. It's possible that the route to deeper understanding doesn't look like more particles at higher energies. It might look like a reformulation of what physics is. Meanwhile, experimentalists keep building. The LHC is upgrading to higher luminosity. Proposals are floating for a next-generation collider, a machine with a ring 100 kilometers around, 3 times bigger than the LHC. China is considering one. CERN is considering one. The United States, after decades of decline in accelerator physics, is looking at smaller specialized projects. Some physicists think the next big collider is essential. Without it, they argue, we have no chance of finding whatever new physics lurks at higher energies. Without it, the field will stagnate. Others argue the opposite. Why spend tens of billions of dollars on a machine that might not find anything? The LHC was justified by the need to find the Higgs, which was predicted with confidence. The next collider has no such definite target. Building it is a gamble on encountering something surprising. The surprise might never come. This debate is happening now. It will shape particle physics for the next generation, and its outcome will depend partly on whether physicists believe the current theoretical framework is close to complete, or whether they believe there's a revolution just beyond reach. It's worth asking plainly, what might replace quantum field theory? If the mathematics is broken, the predictions are accidents, and the physical picture is incomplete, what's the alternative? The honest answer is, nobody has one. Several frameworks have been proposed. None has produced testable predictions that would distinguish it from the current theory. The landscape is full of candidates, none of which has clearly won. String theory replaces point-like particles with tiny vibrating strings. Each vibration mode of a string corresponds to a different particle. The theory naturally includes gravity and unifies all the forces. It requires extra spatial dimensions, 10 or 11 dimensions in total, with the extra ones curled up too small to see. It avoids some of the infinities that plague quantum gravity. It has been the dominant research program in theoretical physics for 40 years. It has also made no experimentally verified predictions. The mathematical consistency of the theory has consumed generations of physicists. The phenomenological predictions depend on how the extra dimensions are curled up, and there are so many possible configurations, estimates range up to 10 to the 500, that the theory can accommodate almost any observation without being falsified. Some critics argue this makes string theory not science at all. Defenders argue it's the best framework we have for quantum gravity, and its predictive ambiguity is a temporary problem to be solved. Loop quantum gravity takes a different approach. Instead of unifying gravity with the other forces, it directly quantizes general relativity. Space-time itself becomes discrete at small scales, made of loops of quantum geometry. The theory is mathematically cleaner than string theory in some respects. It makes some specific predictions about the structure of the early universe and the interior of black holes, but it has its own problems, and it's far from agreeing with the full standard model, and its predictions, where they exist, are typically at scales we can't probe. Asymptotic safety is another proposal. It suggests that gravity, taken as a quantum field theory, is non-renormalizable in the traditional sense but becomes finite at very high energies through a specific structure in its renormalization group flow. If true, it would let gravity be treated by something like ordinary quantum field theory, provided we accept a particular kind of non-trivial high-energy behavior. Evidence for asymptotic safety in gravity is suggestive but not conclusive. Causal set theory proposes that space-time at the smallest scales is a discrete partial order, a network of events with causal relations between them. The smooth manifold we see at large scales emerges from this network as an approximation. The theory has some appealing features but hasn't yet produced a compelling match to observations. And there are more. Non-commutative geometry, twistor theory, holographic approaches like ADS-CFT, which propose that quantum gravity in some spacetimes is equivalent to a quantum field theory without gravity in one lower dimension. Each of these frameworks has advocates, interesting results, and deep unsolved issues. None of them has convincingly replaced quantum field theory. None of them has made a prediction that distinguishes it from the standard model in a way we can test. Here's the uncomfortable possibility that some physicists have started to take seriously. Maybe the true theory of everything is so different from anything we've imagined that none of these frameworks is on the right track. Maybe the revolution, when it comes, will come from a direction nobody is looking. Maybe the person who eventually figures it out isn't alive yet, or is working in a field that currently has nothing to do with physics. Physics has gone through paradigm shifts before. Newton to Einstein, classical to quantum. Each shift was genuinely surprising. Each came from people who were willing to question foundational assumptions that everyone else took for granted. The foundational assumptions of quantum field theory, that fields are the right objects, that space-time is a smooth manifold, that quantum mechanics extends straightforwardly to relativistic systems, might all be wrong. Or some of them might be wrong, or they might be approximately right, but in a way that looks very different from how we currently think about them. Whatever comes next, it probably won't look like a minor tweak to the standard model. It will be a rethinking of what physics is. We've covered a lot of ground. Let me gather the threads. Quantum field theory, as traditionally written, contains mathematical inconsistencies that mathematicians have identified and physicists have not resolved. Hagg's theorem shows that the interaction picture used in every calculation can't be mathematically consistent. Dyson's argument shows that the perturbation series used in every prediction can't converge. The Landau poll shows that the theory taken seriously at high energies eats itself. The vacuum catastrophe shows that naive calculations disagree with observations by 122 orders of magnitude. The mass gap problem, worth $1 million, asks whether the theory even makes mathematical sense, and nobody has been able to answer. And quantum field theory, despite all this, produces predictions of stunning accuracy. 12 decimal places of agreement between theory and experiment for the electron's magnetic moment. Correct masses for hadrons from lattice calculations. Successful predictions of the Higgs mass, the W&Z boson properties, the behavior of quark-gluon plasma in high-energy collisions. The machine works. Nobody disputes that. The panic, then, is not about what quantum field theory gets wrong. It's about what quantum field theory gets right, and why. The theory's success is unreasonable. It's unreasonable by the theory's own lights. Calculations that shouldn't converge give right answers. Procedures that shouldn't be legal produce correct predictions. Mathematical inconsistencies that should break the theory somehow don't. This is the difference between panic and defeat. If the theory was simply wrong, physicists would know what to do. They'd move on. They'd try something else. But the theory isn't wrong. It's right, in some mysterious way that we can't fully account for. And the usual methods of moving forward, improving the mathematics, finding experimental hints, proposing new physics, have been tried and have stalled. Several of our best experimental hopes have recently died. The muon anomaly evaporated in 2025. Supersymmetry has been ruled out in its simplest forms. Dark matter hasn't been directly detected despite decades of searching. The experiments that were supposed to guide us to the next theory haven't found what they were meant to find. Several of our best theoretical approaches have stalled. String theory hasn't produced a testable prediction. The millennium problem remains open. The hierarchy problem, the strong CP problem, the cosmological constant problem, all still unresolved. And so the field sits. Busy, productive, full of working physicists doing good work, but with a quiet awareness that the deep questions haven't moved in a long time. The calculations continue, the experiments continue, the theory keeps working in its mysterious way, but the path forward isn't visible. Some physicists are genuinely despairing, some are genuinely optimistic, most are somewhere in between, focused on their immediate work, hopeful about the long run, aware that progress might require a breakthrough they can't foresee. The panic, if there is one, is private. It happens late at night, when a theorist is alone with a notebook and realizes once again that the theory they've been using for decades has no rigorous foundation. It happens at conferences, inside conversations that don't make it into talks. It happens in the hallway between sessions, when someone asks a simple foundational question and gets an answer that reveals how little we actually understand. There's a quote often attributed to Feynman late in his career. He said that what we're really trying to do is get down to the next layer, and each time we get down there, the problem is harder. Nature isn't simpler at the bottom, it's more complex. We've been looking at quantum field theory for almost a century. We've made it the most successful scientific framework in history, and we've found, at its core, that we don't know what it is. We know it's an effective description of something deeper. We don't know what that something deeper looks like. We don't know how to find out. The predictions keep working, the theory keeps delivering, the questions stay open. That's the panic. Not that our best theory is failing, but that we don't know why it's succeeding, and the usual ways of finding out have stopped producing new clues. One day somewhere, someone will probably have an idea that breaks this open, a new mathematical structure, a new experimental technique, a new way of asking the question. It's happened before, it will happen again. Physics has never stayed stuck forever. Until then, we calculate, we measure, we check, and we wait, quietly, politely, with one eye on the equations and one eye on the dark. The vacuum keeps jittering, The electron keeps turning in its magnetic field. The math stays shaky, the predictions stay perfect, and nobody knows why.